In this chapter, we're going to learn about energy changes, and the whole topic of energy changes revolves around two words. The two words are endothermic and exothermic. So for a start, we need to first define what endothermic means and what exothermic means. Now, endothermic refers to a reaction or process that takes in energy, and this energy is usually taken in the form of heat. So exothermic refers to a reaction or process that gives out energy, usually in the form of heat. So a reaction or process that takes in energy, we call them endothermic reactions. Reactions or processes that give out energy, we say that they are exothermic reactions or processes. Now, one way to remember is this, that endothermic starts with En. So En stands for enter. Enter means taking in energy. Exothermic starts with Ex. Ex stands for exit. So it means energy leaving the system. Now that we have learned the definition, the next important thing is to know how these reactions affect the temperature of the surroundings. Now, in real life, we can only measure the temperature of the surroundings. So when we use a thermometer to measure something, essentially we are measuring the temperature of the surroundings. There's no way in which we can measure the temperature of the atoms or the ions that are undergoing reaction. So we can only measure the temperature of the surroundings. Now, imagine a reaction that releases heat in your vicinity. Alright, so somewhere near you. What will happen to the temperature of the surroundings? The temperature of the surroundings will increase. The reverse is true. If there is a reaction that takes in heat somewhere around you, what will happen to the temperature of the surroundings is that the temperature of the surroundings will decrease. The next important thing that we need to know about endothermic and exothermic reactions are examples, common examples of reactions that are always endothermic and reactions that are always exothermic. So one of them, I think, in daily life, a reaction that's always exothermic, a reaction that produces heat, would be combustion. Other common examples include your acid-base neutralization. So if you have a chance to add a concentrated acid to a concentrated alkali, you will find that the temperature of your container actually increases. Next one would be your metal displacement. Metal displacement reactions are also exothermic in nature. So if you fill the container, it actually gets warmer, or if you fill the test tube, it actually gets warmer. Some other exothermic reactions would include your freezing or condensation. Okay, we have learned this in kinetic particle theory, that when particles move closer together, when particles form strong attractions or stronger attractions, heat is released. So these processes are essentially exothermic in nature. Alright, one last exothermic example would be that of respiration. Okay, when we convert glucose into carbon dioxide and water, it actually produces energy. Now, other examples of endothermic reactions will be this. This is new. You have to remember that dissolving of ammonium salts. Dissolving of ammonium salts are endothermic. So if you have a chance, again, if you add water to ammonium salts, like ammonium nitrate, ammonium sulfate, and if you fill the test tube after that, it's actually cold. Some other examples include your photosynthesis. If you can recall, when we learned about the carbon cycle, we learned that plants actually need sunlight. When a reaction requires energy in the form of sunlight, that reaction would be endothermic in nature. Alright, next, another reaction that we have learned would be your thermal decomposition. Okay, we have learned in the topic of metals that when we apply heat to metal carbonates, they actually decompose into metal oxides and carbon dioxide. So reactions where we need to supply heat, alright, for the reaction to take place, these reactions would be endothermic in nature. And the last example would be your melting or your boiling, evaporation, or even sublimation. Okay, all these processes, if you can recall from kinetic particle theory, that all these processes involve particles being moved further apart. So when particles are attracted to one another, in order to move them apart, we need to put in energy. So these processes are essentially endothermic. Now there are two other examples that are not very common but good to know, which falls under your exothermic reactions. Would be number one, dissolving of anhydrous salts. What are anhydrous salts again? Anhydrous salts are those that do not have water of crystallization. And the other example would be dissolving concentrated acids or alkalis. Now, when you dissolve anhydrous salts or concentrated acids or alkalis, what happens is that they tend to form very strong attractions to water, and the forming of strong attractions to water will outweigh whatever energy required to dissolve them, to break down into their ions. So overall, these reactions are exothermic. So the two additional examples are not common but good to know. So let's try this question over here. The question is asking about how the temperature of your surroundings would change when you dissolve ammonium nitrate in water. So if you can recall from the common examples of endothermic reactions, one of them is the dissolving of ammonium salts. So this reaction is actually endothermic, and endothermic reactions would cause your temperature of your surroundings to decrease. Alright, so that means that A and D are definitely wrong. But let's imagine what happens after we leave the test tube, or after we leave the solution to stand for some time. When we first dissolve the ammonium nitrate in water, the temperature of the surroundings will drop. Okay, but after the reaction, what will happen is that the solution will take in heat from the surroundings and slowly return back to room temperature. Okay, so this is what will happen when we leave a solution to stand for some time. There will be heat exchange with the surroundings until it reaches the original temperature. So the correct answer is B. Now the next thing that we need to learn is known as an energy level diagram. Now what is an energy level diagram? An energy level diagram has only a y-axis, and the y-axis is energy. Okay, so an energy level diagram actually shows the energy level of your reactants and products involved in a reaction. Okay, so for example, if I were to draw a line here and I write reactants, so what this means is that the reactants in this reaction has this particular energy level. So in drawing an energy level diagram, we need to know where is the energy level of your products. If you can recall, an endothermic reaction takes in energy, so your reactants take in energy. So as a result, your products would they have more or less energy than your reactants? If your reactants were to take in energy, your products will end up with more energy than your reactants. So your energy level diagram looks like this, and the energy change in the reaction is represented by this arrow over here. The reverse is true. So when we draw an energy level diagram for an exothermic reaction, this would represent the energy level of your reactants. In an exothermic reaction, your reactants will lose energy. Energy will be given out. So as a result, your products will have lesser energy than your reactants. And the energy change would be represented by this arrow. Now, the amount of energy change involved in a reaction or a process is actually given a special name. It is called the enthalpy change. I repeat, the amount of energy change involved in a reaction or process is known as the enthalpy change. Is given the symbol delta H, and the units will be kilojoules per mole. Okay, so let's look at the energy change involved in an endothermic reaction. If you can see from the energy level diagram, the energy change is a positive one. So for endothermic reactions, your delta H is actually positive. For example, it can be positive 100 kilojoules per mole. The reverse is true. When we look at the energy change for an exothermic reaction, you will find that the enthalpy change or the delta H is negative. So an example would be minus 100 kilojoules per mole. So what do we need to know about endothermic and exothermic reactions with regards to enthalpy change is that enthalpy change for endothermic reactions are positive, and enthalpy change for exothermic reactions would be negative. So this is what was mentioned just now. The amount of energy change in a reaction or process is known as enthalpy change. The symbol is given as delta H, and the units would be kilojoules per mole. Now at O levels, we don't go in depth as to what the per mole means. Okay, so for now, what I would recommend is that if the questions give delta H in terms of kilojoules, then you will write your final answers in terms of kilojoules. If the question gives you in terms of kilojoules per mole, then you write your final answer in terms of kilojoules per mole. Essentially, what does the per mole mean? It means per mole of the reaction. For what exactly does that mean, we will learn that in A levels. So let's try a practice together. In this question, we are looking at the reaction between hydrochloric acid, HCl, and sodium hydroxide. And they tell you that it releases 57.4 kilojoules per mole of heat. So we're supposed to draw an energy level diagram for the reaction. So let's do it together. In an energy level diagram, there's only a y-axis, and the y-axis stands for energy or energy level. And from the description in the question, we can tell that it's an exothermic reaction. So meaning the diagram is going to look like this. Your products will have lesser energy than your reactants. Next, we need to add in your delta H, or enthalpy change, which is minus 57.4 kilojoules per mole. And now, since we know the identity of your reactants and the products in the reaction, we are supposed to write in the actual reactants and products rather than just the word reactants and products. So the reactants in this reaction would be hydrochloric acid plus sodium hydroxide. And what are the products? We have learned in acids and bases that when an acid reacts with an alkali, we get salt and water. Now furthermore, if we can know the state symbols of the reactants and the products, it will be good for you to write it down. So for example, acids and alkalis are always dissolved in water, so they are aqueous. Sodium chloride is a spa salt, so it's aqueous. Water is liquid. Now in drawing energy level diagrams, why is it important to include the state symbols? Is because of this. Now imagine if I were to change water, the state from liquid to gas, do you think the energy change would still be 57.4 kilojoules per mole? The answer is no. Why? Because to convert a liquid to a gas, there's an energy change involved as well. Okay, so this 57.4 kilojoules is for water being formed in the liquid state. So wherever possible, please include the state symbols when drawing energy level diagrams. Now what if you cannot tell from the question, it's not given and you cannot tell, then you don't have to include the state symbols. Now there are actually very common mistakes that students make when drawing energy level diagrams. So look at your energy level diagram right now, if you have drawn them, and see whether you have made the 3 most common mistakes that will be discussed in the next slide. So these are the 3 common mistakes. Common mistake number 1, right? Students will draw your arrow in a way and then it reaches above your products. This is aesthetically pleasing, all right, because your line doesn't intersect with your words, all right. However, this is not allowed, all right, because now your arrow is hanging in mid-air. All right, in drawing energy level diagrams, your arrow must start and end at particular energy levels. Okay, so same thing for common mistake number 2. If you look at common mistake number 2, this is slightly more sinister, because you find that there is a small gap between the arrow, the head and the tail of the arrow, and the energy level diagrams. In cases where we are not so strict, we may actually accept this, but please bear in mind that it has to start and end at particular energy levels. The next very common mistake is this, that students use a double 2-directional arrow to indicate the energy change. Now remember, energy change represents a change, so it increases or decreases. Therefore the arrow must match as well. If it's an exothermic reaction, then it will decrease. If it's an endothermic reaction, then it will increase. So under no situation, under no circumstances should you use a double-headed arrow in an energy level diagram. Now let's try 2 more questions and see whether we can tell whether each reaction or process in each question is endothermic or exothermic. In question number 1, we are given 4 reactions or processes. They are asking you which ones are exothermic. So let's see whether using whatever that we have learned so far, are we able to tell whether each one of them, each stage, is endo or exo. If we look at stage 1, stage 1 involves a change of the substance from solid to liquid. So essentially it is a melting process. Okay, we have learned in the common examples, melting is actually an endothermic reaction, or endothermic process. Stage number 2 is the conversion of the substance from liquid to gas. So this is known as boiling or evaporation, and we have also learned that boiling or evaporation is endothermic. Stage number 3, what reaction is that? We see a substance reacting with oxygen to form carbon dioxide. Now this is a combustion reaction. Okay, and we have learned combustion reactions are exothermic. And lastly, if you look at the last reaction over here, essentially it's not really a reaction, but what is happening is that your gaseous water is being converted to liquid water. So this is your condensation reaction, and condensation, it's not a reaction, it is a process. So condensation processes are exothermic as well. So the exothermic stages would be 3 and 4. The next question, in question 7, they are asking you in which process is energy released. So they are looking for an exothermic reaction. Option A, electrolysis. Where did we learn electrolysis? We learned them in element compounds and mixtures. We have learned in the chapter that compounds can only be broken down by chemical means, and there are 2 chemical means that we have to learn in the syllabus. One is by using heat to break down a compound. The other one is by using current to break down a compound. And if you hear whatever that I've been describing just now, we need to supply energy in the form of heat or current to break down a compound. So A, electrolysis, is actually an endothermic reaction, forming a hydrogen molecule from 2 hydrogen atoms. Now let's take a look at this reaction. 2 hydrogen atoms combining to form hydrogen molecule. So what is happening here is that they need to form a hydrogen-hydrogen bond. Okay, so the formation of attractions or bonds in chemistry, in science, in life, will actually release energy. So forming of bonds, if a reaction involves only bond forming, then it is exothermic. Alright. For completeness, let's look at the 2 other options. Fractional distillation of crude oil. Fractional distillation involves boiling, alright, converting your substances into gaseous form. So essentially it is endothermic. And photosynthesis, we have already learned that it requires sunlight, so it's also endothermic. So the correct answer is B. Now lastly, let's run through this series of reactions and see whether based on your memory of the common examples of endo and exo reactions, whether we can classify them correctly. Okay, reaction number 1 is actually a neutralization reaction, so it's exothermic. Reaction number 2 is a metal displacement reaction, so it's exothermic as well. Reaction number 3, or process number 3, is a boiling process, so it is an endothermic process. Number 4, reaction number 4 is actually a combustion. Again, when something burns in oxygen, when something reacts with oxygen to form carbon dioxide and water, this is a combustion reaction, so it's exothermic as well. Reaction number 5, this one is not one of the common examples, but then if you take a look at what is happening, we are splitting a chlorine molecule into 2 chlorine atoms. So for that to happen, we need to break a chlorine-chlorine bond. So this is the reverse of what we have seen just now. When a reaction involves only bond breaking, to break bonds, to overcome attractions, we need energy. So this reaction is endo. And the last one is what we have seen earlier, 2 hydrogen atoms coming to form a hydrogen-hydrogen bond. So this reaction involves only bond forming, it is exo. Now that we have identified endo or whether the reactions are endo or exo, let's fill in the corresponding enthalpy changes and changes in temperature of the surroundings. Exothermic reactions, delta H is negative. Endothermic reactions, delta H is positive. Okay, for exothermic reactions, your temperature of surroundings will increase. And for endothermic reactions, your temperature of your surroundings will decrease.